Hello and welcome to this video lecture on stoichiometry. In this lesson, we're going to be looking at what stoichiometry is, its definitions, the practical applications of stoichiometry, and then we're going to use those concepts to perform calculations. So to better understand what stoichiometry is, let's take a look at one of my all-time favorite snacks, chocolate chip cookies. So this recipe for chocolate chip cookies tells us that there are 5 ingredients that we need to make said cookies: butter, sugar, eggs, flour, and chocolate chips. This is helpful because it tells me what I need to have in my pantry, but it's not so helpful because it doesn't tell me how much of each ingredient I need to make my chocolate chip cookies. This recipe, on the other hand, not only tells me what ingredients I need to make my chocolate chip cookies, but also tells me how much of each ingredient I need in my recipe. Knowing both the type and quantity of ingredients needed for my recipe is really, really important. Because by changing just one ingredient or changing the quantity of just one ingredient, I can have very different outcomes in my cookies. The other advantage that this recipe has over this recipe is that this longer recipe tells me how many cookies I can expect to make if I follow these particular quantities. So if I have a half cup butter and a cup of dark brown sugar and a half cup of white sugar, etc., I know that I'm going to make 12 cookies. If I need to make 24 cookies, then all I need to do is double my recipe. But because I have very clearly outlined types and quantities of ingredients, I can make predictions about how much I'm going to get or how many cookies I'm going to produce. And if I need to change the amount of cookies that I need to produce, I know how to change my ingredients and in what ratios I need to change my ingredients to get the desired outcome, my desired number of cookies. So what does this have to do with stoichiometry? Well, stoichiometry literally means to measure elements. And stoichiometry is the area of chemistry that uses mole ratios in a reaction to predict or calculate the amounts of reactants needed and or products produced. And what I mean by this mole ratios, what a mole ratio is going to be represented by the coefficients, those large numbers in front of my atoms or molecules in a chemical reaction. So what stoichiometry is going to allow us to do is to make predictions about how many reactants or how much of a reactant we're going to need to produce a certain amount of product, or to calculate how much product we're going to have if we have a certain amount of reactant, or how much reactant will be required if we are producing or if we want to produce a certain amount of product. And in order to make those predictions, we need to look at the quantitative relationships among those reactants and products in the same way we looked at those quantitative relationships in our mole heart. And so we're going to have a map very, very similar to our mole heart, as seen down here, where we have our moles of A, and I can go from moles to liters to grams or to molecules. And over here I have my moles B, where I can go to molecules, grams, and liters. So this map should look very, very familiar because it's essentially just a duplication of your mole heart. And we've taken our mole heart and we've just duplicated it and flipped it. So similar to our mole heart, we can start anywhere on this diagram and go to anywhere else. The additional step is this section right here where I go from moles A to moles B, or from moles B to moles A. And this section here, this conversion factor, so all these arrows stand for conversion factors, and this arrow right here is going to be our mole ratio conversion factor. And that will become clear as to what that is and how we use that when we do some practice problems. But we're going to use this very similarly to our mole heart, so we can start wherever we want and get to any other position on our map using conversion factors. So as with any process in chemistry, we have some steps that we can follow. So for solving stoichiometric equations, step number 1 is to write a balanced equation. Step 2, a balanced chemical equation. Step 2 is to determine the starting point given in the problem. Step 3, identify the number and type of conversion factors needed. And we can determine those by looking at our arrows and the number of arrows between our starting and ending point on our stoichiometry map. And we also need to pay attention to our mole ratio conversion factor if we're going to be using that. And then finally, we're going to solve using the factor label method and conversion factors. Okay, so let's take a look at how this works. So example number 1 asks how many moles of water vapor would be produced from 3.01 times 10 to the 24th molecules of H2. So step number 1 says we need to write a balanced equation for this reaction. So to make water vapor, I know that I have to combine H2, hydrogen gas, plus O2, and I'll get water vapor, H2O. But this isn't balanced because I have 2 hydrogens. 2 hydrogens is okay, but I have 2 oxygens on my reactant side and only 1 oxygen on my product side. So I need to balance my reaction by making this 2 water molecules, and then that balances my oxygen, but I need to make this 2 hydrogen molecules to balance my reactant side and my hydrogen side. So now that I have a balanced equation, step number 2 says to determine the starting point given in the problem. So our factor label method says always start with what you're given. So I've been given 3.01 times 10 to the 24th molecules of H2. And so I'm going to need to multiply by a conversion factor. And I'm going to have molecules, and I'm going to have molecules of H2 on the bottom. And up here on my stoichiometry map, I'm at molecules of A. And so I'm going to go from molecules of A to moles of A. And my A is going to be my molecules of H2, and my B is going to be my moles of water. So not only am I going to be converting between my units from molecules to moles, but I'm also going to be converting between my reactants of hydrogen gas and my product, and going to be converting to my products of water vapor. So I need to be able to make the transfer, and that's where my mole ratio step is going to come in. So I need to determine the starting point, which is my molecules of A, and then I'm going to have 1 conversion factor to get me to moles of A, and then I'm going to do 1 more conversion factor to get to my moles of B, which is going to be my final answer. So when I fill in my first conversion factor, I'm going to have 1 mole of H2 over 6.02 times 10 to the 23rd molecules of H2. So my molecules of H2 have canceled. I'm now in 1 mole of H2. And so on my map, I'm now right here at moles of A. So now I need to get to moles of B, and this is going to be our new step, our mole ratio step. So following factor label method, I know that my moles of H2 need to go down here. And from my stoichiometry map, I know that my moles of B, which in this case I'm converting to moles of water vapor, so moles of H2O, needs to go on the top. So now I need to figure out what needs to go in these 2 spaces. And remember, since it's a conversion factor, these 2 quantities need to be equal. And these 2 quantities I'm going to get from my balanced chemical reaction. Because remember what I said in the beginning of the video, that my mole ratios are actually based upon the coefficients of my reaction. So if I have in my reaction, I have 2 moles of hydrogen gas, and I have 1 mole of oxygen gas, and that produces 2 moles of water vapor. So those coefficients are what I'm going to put into my mole ratio conversion step. So if I have 2 moles of H2, which I do in this reaction, I have 2 moles of H2, and that is going to produce 2 moles of H2O. So my moles of H2 cancel, and I'm left with my moles of H2O, which is what I was trying to solve for. And so when I plug this into my calculator, I'm left with 5 moles of water vapor. So if I have 3.01 times 10 to the 24th molecules of hydrogen gas, I'm going to produce 5 moles of water vapor, which is really handy to know in the lab and to be able to make predictions about how much product you're going to form based on how much reactant you have. So now let's take a look at example number 2, which asks, how many grams of nitrogen are needed to react completely with 25 grams of hydrogen in the reaction below? And step 1 is always to write a balanced equation. And so since they've given us an equation, I'm just going to check to make sure that it's balanced, and it is, so I can actually move on to my next steps. And for factor label method, we always want to start with what we're given. So what I've been given is 25 grams of hydrogen, and in this reaction I'm actually dealing with hydrogen gas, so it's going to be H2. And now I'm going to take a look at my stoichiometry map just so I can get my bearings and figure out how many conversion factors I need based on my starting and ending points. So I'm starting right here at grams of hydrogen, and I need to figure out how many grams of nitrogen I have. So hydrogen is going to be my A and nitrogen is going to be my B. So I'm starting at grams of hydrogen, then I'm going to go through and use one conversion factor to get to my moles of hydrogen, and then I'm going to convert using my mole ratio conversion factor to get to my moles of nitrogen, and then finally through one more conversion factor get to my grams of nitrogen. So now that I have my sort of plan in place, I know where I'm going. Now I can start filling in my conversion factors. So my grams of hydrogen on the bottom, moles of hydrogen on the top, and if I have 1 mole of hydrogen gas, I actually have 2 grams of hydrogen. And now I have moles of hydrogen gas on the bottom, and this is going to be my new step, my mole ratio step, which I'm going to get my numbers from my chemical reaction, my chemical equation. So here I'm going to go from moles of hydrogen to moles of nitrogen. And I want to point out that in this reaction, or in this problem, I'm actually going from hydrogen, which is a reactant, to my nitrogen, which is another reactant. In stoichiometry, we can start at any point in our chemical equation and go to any other point. So I can go from reactant to another reactant. I can go from reactant to product. I can go from product to another product, or I can go back from product to reactant in order to make predictions about what I'm going to produce or what I need. So for my mole ratio step, I look back at my chemical reaction, and I have 3 moles of hydrogen gas, and I have 1 mole of nitrogen gas. So in this reaction, I require 3 moles of hydrogen gas and 1 mole of nitrogen gas to produce 2 moles of ammonia gas. So my moles of hydrogen are going to cancel as my grams of hydrogen canceled. And now I need to keep going because now I'm in my moles of nitrogen, but they asked me for grams of nitrogen. And I know that it's going to take 3 conversion factors. So my moles of nitrogen on the bottom, grams of nitrogen on the top. And if I have 1 mole of N2, I know my molar mass of 1 nitrogen is 14 grams per mole. So my molar mass of 2 nitrogens is going to be 28 grams per mole. And my moles of nitrogen are going to cancel. And the only units and substance that I don't have crossed out is grams of nitrogen, which is what my problem asked me for. And so I do my calculation and I get 116.7 grams of nitrogen are required to react with 25 grams of hydrogen gas. And finally, for example 3, it asks us how many molecules of zinc chloride are produced from 65 grams of hydrochloric acid. So first I want to check to make sure that my given equation is balanced, and it is. So now I want to figure out where I'm starting. So I've been given 65 grams of hydrochloric acid. And now I'm going to look up at my stoichiometry map to figure out where I'm going. So I'm starting at 65 grams. So I'm starting at grams of acid. And I want to go to molecules of zinc. So I'm starting here and I'm going all the way up here. So I'm going to have 1, 2, 3 conversion factors. Because remember, I can start anywhere I want on my map, including at my moles, and go anywhere else. So I can start at grams and quite easily convert to molecules. So my hydrochloric acid is going to be my A, and my zinc chloride is going to be my B. So I'm starting with a reactant. I know how much of a certain reactant I have, and I want to know how much product that's going to produce. So using my factor label method, start with what I'm given. And I'll first convert from grams to moles using the molar mass. Then I need my moles of HCl to go on the bottom. And from my map, I know that I am here at moles of A. So now this is going to be my mole ratio step, where I'm going to convert from moles of A to moles of B, or moles of hydrochloric acid to moles of zinc chloride. And from my equation, from my chemical reaction, I have 2 moles of hydrochloric acid, and that's going to produce 1 mole of zinc chloride. And so now I keep going because I need one more conversion factor to take me from moles of B to my molecules of B. And then finally I can convert from 1 mole of zinc chloride to my molecules of zinc chloride using Avogadro's number. And so when I do my math and cancel out all of my units, I notice that I'm going to go from grams of hydrogen chloride to my moles of zinc chloride, and then finally to my molecules of zinc chloride. So if I have 65 grams of hydrochloric acid, I'm going to have 5.36 times 10 to the 23rd molecules of zinc chloride. So now we're familiar with how to do stoichiometry equations using our steps and our double mole heart or our stoichiometry map to go from any quantity using our mole ratio to convert to any other quantity of reactants to products, reactants to reactants, or even products to products. Bring any questions you have to class and we will go over it together.